Yo, welcome to Physics with Vinay. Welcome back. In this lecture, I'll be teaching you an amazing method to solve complex rotational problems in a single equation without any need for any simultaneous equations. You'll save a lot of time in the exam using this cute method. And to give you an idea of what kind of problems you will be able to solve with this method, these are just four of many problems that you can solve using this unbelievable cute method. So you can see these are complicated looking problems, and if you've encountered these problems in your study of rotational mechanics, you will know that you have to spend a lot of time and effort solving simultaneous equations involving multiple variables, and that often leads to calculation mistakes as well. But once you learn my cute method, absolutely no need for any of that. Just to give you an idea of where this cute method will be applicable, and it's not just these four questions. There are a variety of questions where it will be applicable. And just to give you an idea, you can see, look at this kind of problem where you have a rod and a block, then you have rolling as well as two blocks, and you have a double pulley, and then you have rolling on an inclined plane with a movable plank. So these are just problems where you spend a lot of time and effort solving simultaneous equations, and you won't need to anymore. And not only that, this method is going to have major applications in other chapters, especially SHM as well. So I hope you're as excited as I am. Time to take your rotational mechanics to a whole new level. Let's go! So we'll start off with a simple example and then proceed to more complex ones. So I'm going to take a disc hinged at its center with two blocks hanging and a string going around the pulley. The string is going to be assumed to be massless, but the disc has mass, let's say mass of m, and the blocks have mass m1 and m2. Let's say m2 is greater than m1, and therefore the angular acceleration of the disc is going to be in the clockwise manner. And the question is asking us to find the angular acceleration of the disc. Here in such questions in JEE, we always assume that there is no slipping between the string and the disc. That means there is static friction between string and the disc. That also implies that the tension on both the vertical segments of the string, by which I mean these two blue segments, the tensions will be different. If the tension were equal, then the net torque on the disc would be zero, because the tension torques will cancel each other out, and then of course the disc cannot rotate along with the string. So that will be a contradiction to the assumption that the string is not slipping on the disc. So first let me show the standard method, and then we'll go on to the short method. So in the standard method, we're going to write force equations on the blocks. On each of the two blocks, we're going to write a torque equation on the disc, and then we're going to relate the angular acceleration of the disc to the acceleration of the blocks. So let's say m2 is going down with acceleration a, m1 will therefore go up with acceleration a. Now if I draw the FBD of m1, let's say tension on the left segment of the string is T1, gravity is m1g downwards, so I can write T1 minus m1g is equal to m1a. This is my first equation. Similarly, on m2, I'll have tension T2 and m2g downwards, and because it's going down, I can write m2g minus T2 is m2a. My second equation. Then on the disc, I'll have T1 and T2, and the disc is hinged at the center, and let's say the radius is r, and the angular acceleration is alpha in the clockwise direction. So the net torque in the clockwise direction on this disc is going to be T2r minus T1r. You can see T2 ka torque is going to be clockwise, T1 ka torque is going to be anti-clockwise. So the net torque in the clockwise direction is going to be T2r minus T1r, should be equal to the moment of inertia of the disc would be mr square by 2 times alpha. This will be my third equation. And the last equation is, because there is no slipping between the string and the disc, the acceleration of the string and the acceleration of the circumference of the disc should be equal. Now acceleration of the string is nothing but the acceleration of the blocks, and acceleration of the circumference of the disc will be alpha r. So I'll have a is equal to alpha r. So you have 4 simultaneous equations, and you can solve 4 simultaneous equations to get those 4 unknowns, which is T1, T2, alpha and acceleration. So this is the standard method in order to solve this kind of a problem. Now let's look at a cute method where you'll only need to solve one equation. Let's take a look. The key to this cute method is to recognize that the string length has no role to play. The string length has no contribution to any of the equations that we wrote. So what I'll do is I'm going to shorten the string length and I'm going to make it exactly 0, and therefore what I'm going to effectively be doing is I'm going to stick these blocks onto the circumference. So I'll have M1 and M2 on the circumference of the disk. Here basically what I've done is I've assumed that the string length is 0, and therefore those 2 blocks are like 2 particles stuck to the disk. So for that particular instant, they can be treated as part of the disk itself. And now you have your gravity forces. Now I can simply write torque equation as m2g into r minus m1g into r, once again in the clockwise direction, should be equal to I alpha, where moment of inertia of the disk is mr square by 2. But here's the key point: you have to include the moment of inertia of the 2 red particles, which are representative of the blocks. So what is happening is these 2 red particles are now part of the disk. So the moment of inertia, I can write it as m1 r square plus m2 r square, and this is the entire moment of inertia times alpha. That's it. One equation and you get alpha. So hope you've understood this cute method. The entire method is based on the concept of sticking the blocks onto the circumference of the disk, and the logic behind that is the string length has no role to play. So we are eliminating the tension variables directly. Once you eliminate the tension variables, you're just left with one equation in order to get the angular acceleration. Here I want to point out one thing, that some people teach this concept of rotational mass, this so-called shortcut method, where they use the concept of rotational mass and then write a force equation. They define rotational mass as I by r squared, and you can also use that method to get the solution for this problem in one equation. However, that is a very limited method. It is not applicable to questions where you have double pulleys and where you have rolling. Basically, it's very limited in its applications. So that is not the method that I am teaching or I am going to be using. Every question that can be solved using that method can also be solved using mine. And my shortcut method can solve a lot more questions. So please don't confuse that rotational, so-called rotational mass method with my method. Now let's start increasing the complexity of problems. Let's take a look at another problem now. So this time I have a double pulley. And let's say the masses are 2m and m. And the double pulley is like a spool. So it's like this inner, you can call it a ring or maybe an inner disc, is stuck to that bigger disc. So it's all part of one rigid body. Everything is moving with the same angular velocity and same angular acceleration. So let's say the outer radius is r, and let me give the inner radius as r by 2. Now the question is asking, find the angular acceleration of this pulley. The question will also give you the moment of inertia of this double pulley, and let's say that moment of inertia is given as mr square by 2. This is of the pulley about its hinge. So this will be given to you in the question. So I suggest that you give it a try now. Use the cute method, stick the 2 masses on the circumference of their respective discs and write down the torque equation. Don't forget to include the moment of inertia of the particles themselves, because they'll be part of the pulley now, and you should be able to get the angular acceleration. So pause the video, give it a shot, and then you can take a look at my solution. Okay, so hope you've given it a try. So let me show how we can solve this question using the short method. So what I'm going to do is I'm going to once again stick the two blocks onto the edge of the pulley. So I'll have a 2m here and an m here, and the forces will be 2mg and mg. And now I can write my torque equation. So in the anti-clockwise sense, I can write 2mg times r about the hinge minus mg times r by 2. The distance of m is r by 2 from the hinge. So this is the net torque in the anti-clockwise sense, should be equal to I alpha for the pulley is given to us as mr square by 2. And what about the particles? I'll have the distance of 2m is r from the hinge, so that will be 2m times r square plus the distance of m is r by 2. And the entire moment of inertia times the angular acceleration. So the first term in the moment of inertia is for the pulley, the second term is for mass 2m, and the third term is for mass m. And that's it. Just solve for angular acceleration and you should be able to get it as 6g by 11r. So you can see the powerful nature of this cute method. No simultaneous equations anymore. One equation, get your angular acceleration, and hope you've understood how to solve these kind of questions. Now I'm going to show you a variety of questions where this can be applicable, and you'll be amazed to know that it's not just this kind of pulley problems. There are plenty of other problems where this cute method is going to make your life really easy. Let's take a look at another question. This problem is going to be a little different. I have a disc attached or hinged at the corner of a table, and I have a string going around the disc. The mass is m. Let's say I have another block attached hanging vertically, and let's say the disc also has mass m. So once again, no slipping between the string and the disc, and let's assume the table is smooth. The question is asking us to find the angular acceleration of the disc. So give it a try. Use the cute method once again. Stick the masses onto the circumference of the disc and write the torque equation. You should be able to get the answer, and then you can have a look at my solution. Alright, so assume you've given it a shot. Let's take a look at the solution and let's see if you've gotten it right. So once again, I'm going to stick the blocks onto the circumference of the disc. So I'll have a mass m on the right hand side and a mass m at the top. Now in order to see what effect gravity has for the block on the table, and we had seen this concept in the first lecture of laws of motion, if you remember, that the gravity here is perpendicular to the string and normal force will cancel out. We are actually looking at only forces along the string. So there's no component of gravity for the block on the table along the string. So that will not make an appearance in our diagram where we stick the blocks onto the disc. So the only force that will apply a torque will be the gravity of the right hand side block, and therefore I will have mg times r is my torque and should be equal to moment of inertia into alpha. So moment of inertia of the disc will be mr squared by 2 about its hinge, and for the particles they'll both be mr squared and mr squared times alpha. That's it, and you will get angular acceleration as 2g by 5r. And if they ask you the acceleration of the blocks, that will simply be alpha r, which will be 2g by 5. So you can see once again, short method, no simultaneous equations, one equation and you get the angular acceleration. Now let's do that question with a block on the table, but this time with friction involved. Now let's see how friction plays a role here. So in this question, I have a block attached to a string which is going around a disc and then attached to a block hanging vertically. Both the blocks and the disc have the same mass m. So it's like the question that we did earlier, but the only difference is that the table is no longer smooth. It has a coefficient of friction mu given to us. So the question is asking find the angular acceleration of the disc. So you can use the cute method and you can try it out on your own and then look at my solution and see if you've gotten it correct. Okay, so we'll do the same thing. We'll stick the blocks onto the circumference of the disc. I'll have a mass m here and a mass m at the top. So we saw in our previous example of this sort that mg and normal force get cancelled out. Mg has no component along the string. Remember, we write forces ka components along the string. So the only mg will be acting on the right hand side block. However, on the upper block, I will have a frictional force acting to the left. So that friction is entirely along the string. So in our diagram where we stick the blocks onto the circumference, my friction F will be acting in this manner. So I hope you've understood how I have drawn the diagram for the cute method and the forces as well. So now first thing is, if the torque of gravity is able to overcome the torque of friction, only then is the system going to be in motion. So for the upper block to slip and therefore the system to be in motion, the torque of mgr should be greater than the torque of friction. And here friction will be taking as the maximum possible friction, and therefore mg should be greater than mu mgr. So as long as mu is lesser than 1, this disk is going to rotate and the upper block is going to slip. So if mu is greater than 1, then alpha of the disk is going to be 0. There is no motion. And we look at the case where mu is less than 1. So for mu less than 1, I'll have my net torque in the clockwise direction would be mg into r minus friction into r. Now here friction will be the kinetic friction. There will be mu mg into r should be equal to moment of inertia into alpha. Moment of inertia for the disk is going to be mr squared by 2 about the hinge, and for the particles mr squared plus mr squared because they are at a distance of r from the hinge times alpha, and therefore you will get your alpha as 2 into 1 minus mu g by 5r. So this is your angular acceleration. So here you see how we can solve questions involving friction as well using the cute method. So the question here involves a rod hinged at its left end and it's connected to a string at the right end which goes over a massless pulley, and the string is connected to a block which is hanging vertically. So the question is asking us to find the acceleration of this block. Now what we're going to do is we're going to do the same thing that we did so far. We're going to stick the block this time onto the end of the rod. So let's take a look. So if you want, you can give it a try, but this is a slightly different question. So once you give it a shot, do take a look at my solution. Okay, so I have this block and I'm going to take it over the massless pulley and I'm going to stick it to the rightmost end of the rod. In doing this, the important thing is to realize that the gravity that is acting vertically downwards is also going to rotate. So we are rotating the block as well as the gravity in the anti-clockwise sense. So once I make the diagram of the rod and the block, it will be like I'm sticking this block, and because I've rotated this block in the anti-clockwise sense by 180 degrees, the gravity will also rotate. Once again, this is very similar and this is exactly the same concept that I taught you in the laws of motion lecture, where we used to rotate blocks and strings, and along with that we had to rotate the forces as well. So you have this rod hinged at its left end, and the key point is to realize that you have a particle stuck to the right end, which is basically the block, and the force acting on the particle is now mg in the upward direction. That's the main thing here. And of course we'll have an mg for the rod as well in the downward direction acting at its center of mass. So you can see that the net torque will be in the anti-clockwise sense. So I can write my torque as, let's assume a length L for the rod. My torque will be mgl. This is in the anti-clockwise sense by the gravity of the particle minus mgl by 2. This is the clockwise torque by the gravity of the rod. And this should be equal to I alpha. Moment of inertia of the rod is going to be ml squared by 3 about its end. And don't forget, we have to include the moment of inertia of the red particle as well. So that will be ml squared times alpha. That's it. So you will get alpha as 3g by 8l. Now what will be the acceleration of the block? Was basically the acceleration of this red particle here, and that's at a distance L from the axis of rotation, so that acceleration is going to be alpha into L. That will be 3g by 8. If you look at the direction, since the rod is rotating in the anti-clockwise sense, the string attached to the rod is going to travel upwards, and therefore the block is going to travel downwards. So the acceleration of the block is going to be 3g by 8 in the downward direction. So hope you've understood this question as well. Once again, we've eliminated the need to solve simultaneous equations. We've eliminated the need to involve tension of the string by simply reducing the string length to 0. Now let's look at a question where inclined plane is involved. So here I have a fixed inclined plane on which I have two blocks connected by a string. The string is going around a massive disk of mass m, and the question is asking us to find the acceleration of the blocks. So once again, you can stick the masses on the circumference of the disk and write the torque equation. I would encourage you to try it out once before you take a look at my solution. Alright, so I know that the forces acting on the blocks along the string would be m1g sine theta 1, and here it would be m2g sine theta 2. Now let me assume that the disk is rotating in the clockwise sense. This is an assumption. If we were given the values of m1, m2 and the angles, then finally when we get the value for alpha, if it is negative, then it is in the opposite direction to what we had assumed. So now what I'll do is I will stick the masses onto the circumference of the disk like we've done in all of our previous problems, and therefore here I'll have m1g sine theta 1 and m2g sine theta 2. I'm only concerned with the forces along the string because the normal component of gravity would anyway be cancelled out by the normal force by the inclined plane. And let's say the radius of the disk is r, so my torque equation would be m2g sine theta 2 times r minus m1g sine theta 1 times r. So this is my net torque on the system, and therefore I can write this as moment of inertia times alpha. So moment of inertia for the disk would be mr square by 2 hinged at the center, and the particles are at a distance r from the center. So I can write m1r square plus m2r square. That's it. You can get alpha, and the acceleration of the blocks will simply be alpha r. So hope you guys were able to do this question, and if not, hope you've understood the solution. Let's do another type of question. So this is a slightly different question from what we've done so far. I have a block. Once again, the surfaces are all frictionless. I have a block attached to a string going around a massless pulley, and then it's going around a disk of mass m and radius r. The string is connected to a fixed ceiling. The question is asking us to find the angular acceleration of the disk. So try it out before you take a look at my solution. Alright, so let's take a look at how we will solve this using the short, the cute method. I'm going to stick the block M once again, going over the pulley. I'm going to stick it on the circumference of the disk. So my diagram will have a block M here. There will be no gravity component of the block M because the gravity is perpendicular to the string anyway. Mg and normal force are anyway cancelling out and perpendicular to the string, so no component of gravity is going to come along the string. And I have a gravity for the disk. Now, in order to avoid the tension of the right portion of the string, I want to avoid that. I don't want to have an extra variable for that. So I'm going to write the torque equation about the instantaneous axis of rotation. Now here the instantaneous axis of rotation is just a fancy name for the point which is at rest. Because we always assume there is no slipping between the disk and the string points are all at rest. Therefore the point of the disk, the rightmost point, let's say point P, which is in contact with the string, that will also be at rest. And if it's at rest, that means it is on the axis of rotation. So at that instant, point P is my axis of rotation. So let's try the torque equation. The torque of gravity of the disc would be mg times r about point P. Gravity is making a distance of r from point P. And that should be equal to moment of inertia. So for the disc, I'm going to be using parallel axis theorem. About the center, mr square by 2 is the moment of inertia for the disc, plus md square, where d is the distance between the center of mass and point P. So that will be the radius itself. That will be mr square. So this will be the moment of inertia of the disc about point P, plus don't forget the moment of inertia of the red particle. And the red particle, which is basically the block, is at a distance of 2r from point P. So that will be m times 2r the whole squared. And this is the entire moment of inertia, so I'll multiply it by angular acceleration, and that's it. You will get angular acceleration as 2g by 11r in a single equation with no simultaneous equations at all. So you should be able to really appreciate the amazing, powerful nature of this cute method. If you were to do this question using the standard method, just have a look at the number of variables that you will have to involve. You will have a tension T1, a tension T2, alpha of the disc, acceleration of center of mass of the disc, and the acceleration of the block. You will basically end up with 5 variables and therefore 5 equations. And we've just solved the entire problem in a single equation. Now a query might arise in your mind: what if the question asks us to find the acceleration of the block or the acceleration of the center of mass of the disc? What then? That is very simple, because you know the angular acceleration of the disc. We already calculated that here, and therefore the acceleration of the center of mass, since it is at a distance r, that will simply be alpha r. Then you can ask me, what is the acceleration of mass m? Since mass m is at a distance of 2r from the axis of rotation, the acceleration of block m would be alpha into 2r. That's it. It's as straightforward as that. In all such questions, if you are able to get angular acceleration, everything else will just be extremely easy in terms of alpha. So hope you've understood these kind of questions, these kind of pulley problems. Now let's take a look at a similar question which is slightly different from what we just did, but you should be able to solve it on your own. So I have a block of mass m connected to a string which is going around the massless pulley, and then it is going around a disc of the same mass m which is connected to a ceiling. And the question is asking us to find the acceleration of the block, or find the magnitude as well as the direction. So do it like we did the previous question, give it a try, and then you can have a look at my solution. Okay, so I'll do what I've done in all my previous problems. I'll stick this block M going with the pulley, I'll stick it to the left end of the disc. So I'll have a particle of mass m stuck here. Now gravity, which was acting downwards, will be acting in the upward direction. It is exactly like how we had done these kind of situations where we rotated the block in the lecture on laws of motion. If you remember our lecture from laws of motion chapter, you will understand this perfectly, on how we have rotated the block and therefore the gravity in the clockwise direction. And then of course I have a gravity for the disc as well. And once again, what will be the instantaneous axis of rotation? The instantaneous axis of rotation is the point which is at rest. Now the point of the disc which is in contact with the string will be at rest, because we always assume in such questions that there is no slipping. So since the string is at rest itself, the point of the disc will also be at rest. So that will be my IOR, which is the instantaneous axis of rotation. And now it's a very simple case of simply writing the torque equation about the IOR. So first off, you should be able to see the direction of angular acceleration, because the gravity of the particle will have a greater torque about the IOR. It is at a greater distance. The net angular acceleration will be in the clockwise sense. So my torque equation will be mg times the distance is 2r minus mg times r. This will be the torque due to the gravity of the disc in the opposite sense, should be equal to I alpha. So for the disc, that will be mr square by 2 plus mr square by parallel axis theorem, plus For the particle, there will be m into 2r the whole square. So at a distance of 2r from the I1, and this entire moment of inertia times alpha, and you should be able to get your alpha ka value as 2g by 11r. Now this is my angular acceleration. The question is asking the acceleration of the block. So because the particle which is representing the block is at a distance of 2r from the I1, the angular acceleration is alpha, so the acceleration of the particle m would be alpha into 2r, and therefore acceleration of the block would be 4g by 11. Then what about the direction? Because the angular acceleration is in the clockwise direction, the leftmost end of the disk is going upwards, and therefore the block will be going downwards. So the block has an acceleration of 4g by 11 in the downward direction. Hope you guys have understood how we can simply avoid simultaneous equations to solve such problems. We avoided the tension in the string, we've avoided the tension in the right portion of the string. We haven't done any sort of simultaneous equation calculations. In this question, we have a spool of outer radius r and inner radius r by 2, and I have a block of mass m hanging from the outer circumference of the spool. The spool mass is given to be m, and the moment of inertia of the spool about its center is given to be mr squared by 2. Now the question is asking us to find the angular acceleration of the spool and the acceleration of the block. So figure out where the instantaneous axis of rotation will be, and then use the cute method. Give it a try, and then you can take a look at my solution. So first thing that we'll have to do is figure out where the instantaneous axis of rotation is. That will be at the intersection of the string and the spool. So this blue point, that will be my axis of rotation at that instant. And we know that we always assume that there's no slipping between the string and the spool. So the point of the spool in contact with the string will also be at rest. So that will be my instantaneous axis of rotation at that instant. And now we'll use a cute method. We'll stick this block onto the circumference of the spool. So I will have a particle of mass m, which is representing the block, stuck onto the circumference, and this blue point will be my axis of rotation. Now let's write the torque equation about the axis of rotation. I'll have gravity of the particle, and that is at a distance of 3r by 2. So I'll have mg into 3r by 2 in the clockwise sense. Then I'll have the torque of gravity by the spool, and that is at a distance of r by 2. So plus mg r by 2 should be equal to I alpha. So moment of inertia of the particle is going to be m into 3r by 2 the whole squared, plus moment of inertia of the spool about its center is given to be mr square by 2, plus I'll have another term using parallel axis theorem of m into r by 2 the whole squared. So this entire thing is spool, and the first term is the particle, which is the block. So entire moment of inertia times alpha, and you should get your angular acceleration as 2g by 3r. So this is my angular acceleration in the clockwise sense. The other thing that the question is asking us to find the acceleration of the block. The block, which is basically the red particle, is at a distance of 3r by 2 from the axis of rotation, and therefore my acceleration of my block is going to be alpha times 3r by 2. So that will be equal to g downwards. And that's it. So you can see how we've used the cute method in order to solve such questions. So we have not even talked about the tension in either of the two strings. If you do it in the traditional way, you'll have to involve the tension in this blue string, the tension in this red string. That will be two variables. Then you'll have to involve the acceleration of the block, the acceleration of the center of the spool, and the angular acceleration of the spool. You can see that will be like 5 variables and 5 equations. So a lot of time and effort has been saved using this cute method.